Welcome to the GEOTOP-A webinar series. Our speaker today is Darrick Lee of the University of Oxford. He's going to talk about mapping space signatures. Take it away, Darrick.
Yeah. Thank you very much. So first, I'd like to thank the organizers for inviting me to speak here today. I'm very excited to talk about this work that is done in collaboration with Chad Giusti, who's just moved to Oregon State University, with Vidit Nanda at Oxford, as well as Harold Oberhauser at Oxford. And just to start off with some motivation, the theme of this talk is to study certain types of feature maps for data. So let's suppose that we have some topological space X, and this is some space of data that we would like to study. One way of studying this data is by applying some feature map. This is just some map from our topological space X into some linear space. Often it's useful to have some sort of inner product structure, and so it's useful to think about this codomain as a Hilbert space. Now, we can often classify some problems in machine learning into sort of two different categories. Either we want to study some sort of functions on our input space X, or we want to study measures on this input space X. And there are two properties that tell us that this is a good feature map in terms of these two problems. So the first is universality. Now, the map phi is said to be universal with respect to some function class, f. So for instance, you can think of f as the space of continuous functions from x into r, for instance. So we say that this feature map phi is universal with respect to f if the linear functionals on the Hilbert space, sort of viewed as functions from x into r, if these functionals are dense in our input space. Are dense in this function class. Now, what this allows us to do in sort of more practical contexts is to turn nonlinear problems into linear ones. So if we're able to sort of approximate any continuous function using linear functionals, this allows us to turn, for instance, a nonlinear classification problem into a linear classification problem. On the other hand, if we want to study measures on X, we would like the feature map to have another property of characteristicness. So we say that the feature map phi is characteristic with respect to the probability measures on X if the expectation of this feature map is injective. So the input here is a probability measure. We take the expectation of the feature map with respect to this, and we get an element of the Hilbert space. So this turns a fairly complicated object into just some element of a Hilbert space, and we have a natural notion of a norm there. This means we can define and compute things like distances between probability measures, and it allows us to do things like hypothesis testing. Now, in this talk, we're going to be focused on a certain type of input space X, and that is the case where X itself is a space of maps. So we can think about this as some sort of parametrized data. So one data point is going to be a map from some domain D into some state space Z. So for instance, D could be just the unit interval from 0 to 1, and these would just be time series data. The domain could be some unit D cube. So for instance, if D is equal to 2, this could correspond to images. If D equals to 3, then perhaps these are videos we're looking at. Could also have more complicated cases where D is some graph or simplicial complex. On the side of state spaces, we could be interested in just the case of Euclidean data. Maybe our data has some sort of, is geometrically valued, or we could be studying things like point clouds, in which case things like persistent homology would come up. And the overall goal is to develop feature maps that somehow preserve the structure of this parametrized data. So for this talk, we're going to be looking at the case of maps from the unit d cube into Rn. So in particular, we're going to be restricting ourselves to Lipschitz maps. This is just to have some notion of regularity so we can do things like perform integrals. Now, this specific case has wide applications, right? When d is equal to 1, we already have time series. In d equals 2, we can look at things like images. And mathematically speaking, this is also sort of an interesting generalization of the case of d equals 0. So if d equals 0, Lipschitz maps from a single point. I'll say that the 0 cube is just a single point. This mapping space is just Rn. And a very canonical feature map to use here is just to take all of the possible monomials on Rn. It turns out that there is a construction in the case of d equals 1. So if we're looking at Lipschitz paths in Rn, this is called the path signature. And our goal here is to generalize this path signature construction to higher dimensions, which is the title of this talk, to develop this notion of mapping space signatures. So I'm going to split this talk up into 3 sections. I'll start off by introducing path signatures, which is by now a fairly well-studied area. And then I'll talk about how this actually originates from Chen's cochain model, cochain construction for loop spaces. And finally, I will talk about how this motivates a definition for the mapping space signature and give some of their properties. So let's just focus on the case of d equals 1 for now and think about Lipschitz paths into Rn. And this is the case of looking at time series. So to motivate this construction, let's look at an example. Let's suppose that we want to look at this time series data. So here we have 2 time series, dark blue and light blue, and we want to somehow understand relationships between these time series. Qualitatively speaking here, we can see that there is some sort of lead-lag behavior going on. The dark blue time series is leading the light blue. And we can quantitatively study this using classical techniques such as cross-correlation. This is just taking the convolution of these 2 time series. So by looking at the cross-correlation, what we can see is that there are certain peaks that arise, and the existence of these peaks gives us some idea that there is some sort of lead-lag behavior going on, and in particular there's some time delay between these 2 signals. However, one downside to cross-correlation is that it's dependent on the parametrization of these time series. So if I reparameterize, right, this original nice peak that we have here, it gets flattened out, and we can no longer detect this lead-lag behavior, even though it's still there. And the reason behind this is that the existence of lead-lag behavior is something that is reparametrization invariant, whereas cross-correlation is dependent on this parametrization. So one method to sort of alleviate this is instead of looking at these time series directly, I want to think about these time series as a path in R2. So all I'm doing is I'm plotting gamma 1 against gamma 2, the 2 components of the time series. If I reparameterize, the image of this path doesn't change at all, it just changes the velocity. And instead of directly looking at the time series, we can study geometric properties of this path, such as its signed area. And this can be used as an indicator of lead-lag behavior, which is reparameterization invariant. So it turns out by just a sort of basic application of Stokes' theorem that I can rewrite this signed area as the linear combination of these 2 iterated integrals. And I'm going to suggestively call this S12 and S21 of gamma. So these are these 2 components of this integral. And it turns out that these 2 terms, S12 and S21, are just part of a much richer structure, which is called the path signature. And so let's give the full definition of this now. So let's suppose that we have some Lipschitz path. This is now n-dimensional. So in the time series setting, this just corresponds to having n simultaneous time series. We'll take some multi-index I. This is just a collection of m numbers ranging between 1 and the dimension of the path n. We say that the path signature of x with respect to I is this iterated integral. So here we are integrating the derivatives of the path, the components of the derivatives of the path specified by these coordinates given by the multi-index. And we're integrating over the standard m simplex. So this is t1 less than t2 up to tm. And we can collect the path signature with respect to all multi-indices I by viewing the path signature of x as a map from these Lipschitz paths into the completed tensor algebra. So we can think about this as just a sequence of tensors of increasing degree, or you can think about this as formal power series of tensors. So just formal power series where the variables are non-commutative. And we just place the path signature with respect to I as the coefficient in front of one of these basis elements. So just to be precise, if E1 up to En is a basis of Rn, then I'm just denoting this EI1 tensor up to EIM as a basis of the mth tensor product of Rn. So this object was originally defined by Chen in the 50s, and his original motivation was to study and characterize paths on manifolds. And then later developed this theory of iterated integral cochain models for path spaces and loop spaces, which I will get to a bit later on. But in the 90s, this path signature was once again studied by Terry Lyons, but in a completely different setting. In this work in 98, Terry Lyons started to develop this theory of rough paths. And this is now become a fairly influential field in stochastic analysis. And we can think about this as a theory of deterministic integration for highly irregular paths. So these are things like Brownian motion or even more irregular. We won't go into the stochastic analysis at all today, but I think it's important to have this sort of point in mind. So now I'll go through some of the basic properties of the path signature. There are certain invariance properties that the signature has. The first is translation invariance. So if I take a path and I take some vector Rn, some vector A, then the signature of x is independent of the translation, is invariant under translation. And this is just because we're only integrating derivatives, and the derivatives themselves are translation invariant. And I will denote translation equivalence classes paths by lip j. And the reason for this j will become apparent later on. And the second invariance property is that it's reparametrization invariance. This is what we started off with in motivation. So if I take some path and some reparametrization of the time axis, then the signature is going to be invariant with respect to this. And it turns out that the full invariant structure of the path signature has been characterized. And this says that if we take two paths, x1 and x2, then their path signatures are the same if and only if they are tree-like equivalent. So I'm just going to define this by using a picture. So let's suppose that we have these two paths. Let's say on the left, this is x1, and on the right, this is x2. We say that these two paths are tree-like equivalent if they differ by a finite number of these branches. So here, the first path on the left It traces out alpha, which goes up to this point. It goes along zeta, and then retraces along back along itself, and then goes on to beta. So we can think of this zeta concatenated with zeta inverse as sort of a branch, and if two paths differ by a finite number of these, then we say that they're tree-like equivalent. So this definition only holds if the paths are sufficiently regular. So for instance, piecewise C1. And this was originally proved by Chen in the 50s, but later on proved by Ben Hambley and Terry Lyons in 2010 in the case of bounded variation paths. There's also some algebraic properties of the path signature. And there's sort of, there's two different algebraic properties of the path signature. There's the shuffle product and what's called Chen's identity. What the shuffle product says is that if we have two different terms of the path signature, let's say indexed by I1 and I2, then the product of these signature terms can be written as a linear combination of these higher order terms. So in particular, these higher order terms are indexed by what are called shuffles. And so just to have an example here, let's say that we want to multiply phi1 with phi2, 3. All we're doing here is we are shuffling the multi-index just consisting of single element 1 with the multi-index 2, 3. So we're just moving 1 in between in all of the possible places between 2 and 3. Now the main point I want to make here is that these signature terms, phi I, by I I mean the multi-index I, these signature terms form a subalgebra of continuous functions on the path space. And this gives us our first indication that these signature terms act something like ordinary monomials for a Euclidean space. And we'll get to this more on the next slide. But first, I also want to highlight the second algebraic property, which is Chen's identity. So if I have two paths, say alpha and beta, I can look at the concatenation of these two. And the path signature preserves this concatenation structure. So the signature of the concatenated path will be the tensor product between their two signatures. And so the last property I want to discuss is universality and characteristicness. These were the two properties that I mentioned at the very beginning. And I want to do this by highlighting this connection to monomials. So in the case, recall that in the case of d equals 0, so this is the case where this Lipschitz mapping space is just Rn, I can define the monomial map, which is just taking tensor powers of any given vector. In practice, this turns out to just be the collection of all possible monomials. In the case of d equals 1, we have a very similar we have a similar construction called the path signature. And in these two cases, if we perform some normalization procedure, then it turns out that both of these maps are universal with respect to continuous functions. And the space of continuous functions has to be equipped with something called the strict topology. But the point here is that we can approximate continuous functions on the entire either Rn or the entire path space using linear functionals on this tensor algebra. It's also characteristic with respect to probability measures. And so this implies that we can characterize the laws of random variables either on Rn or on path space. So these a probability measure on the path space can be thought of, in this case, as a stochastic process with Lipschitz samples. And our goal is to develop this signature type object for cubical mapping spaces in the case of d greater than 1. So before I move on, I want to highlight that these two properties in the case of Rn are very classical results if we take the case, if we suppose that we have a compact subset of Rn. If we have a compact subset of Rn, we know that polynomials are dense in the space of continuous functions. This is just the classical Stone-Weierstrass theorem. And if we have compact, and characteristicness says that that the moments of a compactly supported random variable is characterized, it completely characterizes the measure. And so both of these were, in this case where this extends to the whole space, Rn, and this path space setting, this was proved by Ilya and Harold in their recent paper. Okay, so in order to define a generalization of path signatures to a higher dimensional setting, we're actually going to return to Chen's original construction of his cochain complexes. And this will give us some way of defining these mapping space signatures, which hopefully will have similar properties. So Chen's construction is a way of studying smooth path spaces and loop spaces. So in this section, I'm going to denote PRN to be smooth paths from the unit interval into Rn, and this is just to be able to talk about things like differential forms without having any difficulties. So Chen's construction is a way of taking a collection of differential forms on Rn and constructing a differential form on the path space of Rn. Now, okay, there's some subtlety here because the path space of Rn is infinite dimensional and so is not a manifold. And Chen developed this theory of differentiable spaces, which allows us to talk about differential forms on things like infinite dimensional spaces. This is very similar to these diffeological spaces, which I think are a bit more common now. So on this point, we won't need to go into this in any details. We can just think about differential forms on path space as some analog of differential forms in infinite dimensional space. So it turns out that the path signature, these path signature terms arise as certain zero forms in this Chen's construction. So if we choose specific differential forms, we'll get a certain zero form out, and these are exactly the path signatures. So just to give some references, these are two references originally by Chen in the 70s that developed this theory. And here he was primarily interested in geometric ways of studying loop space cohomology, so some sort of de Rham theoretic way of studying this. And very soon afterwards, this construction was extended to mapping spaces, so to look at cohomology of mapping spaces from a more geometric perspective. And all of these constructions are based on using simplicial sets. So let's go through what this construction is in a bit more detail. And we can think about this as something that happens in 3 steps. So first, so here X is, we'll just take X to be some manifold. First, let's choose some collection of differential forms, omega 1 up to omega m, on our manifold. These can be differential forms of differing degrees. We compute the pullback of the tensor product of these forms along what's called the evaluation map. So this is a map from the standard M simplex across the path space of the manifold into M copies of the manifold. So what we're doing here is we're just evaluating the path at these M coordinates specified from the simplicial complex. So when we pull it back, we now have a differential form on delta m cross px, and then we can integrate the resulting form along the delta m component. We can also do this more explicitly to see what's going on if we look at the case of x equals Rn, and we choose our differential forms to just be standard 1 forms. In this case, we can explicitly compute this pullback. We'll get just a product of derivatives of our path, where the components are specified by which differential forms we chose. And when we integrate this differential form along the M simplex, we recover these path signature components. So what we want to do is to use this construction to give us a generalization of this path signature. And now the main thing that we need to generalize is this evaluation map. How do we define something like this evaluation map when we don't just have paths? And this is where we have to go into the more recent works on Chen's construction for mapping spaces. But our primary domain of interest are unit D cubes. And the reason for this is that in practice it's much more common to have maps that are parametrized by squares or cubes rather than simplices. And so the first step of what we had to do was to reformulate this work on Chen's construction on mapping spaces into the language of cubical sets, which are really just an analog of simplicial sets, except we're using cubes rather than simplices. So let me just briefly go over how this construction works. So a finite cubical set, we can think about this as some model, some combinatorial model of the unit D cube. So we'll denote this cubical set Z dot. This consists of some finite sets, ZP, and you should think about these elements of ZP as the p-dimensional components of the space. So there's more formally, we can think about this as a certain contravariant functor from a certain box category. Here, the objects are just elements of the natural numbers, and for each, and the morphisms are generated by these 3 types of maps. If you're familiar with simplicial sets, this should look quite similar, except we now have these co-connection maps, which should be thought of as an extra type of codegeneracy. And we can think about these 3 types of structure maps as just part of the information contained in a cubical set. So, for instance, coface maps are just ways of identifying cofaces of any element in these cubical sets. And coded degeneracies give us ways to talk about degenerate cubes. And so let me give an example of what a cubical set looks like. So if we are just thinking about a unit interval, there are going to be 2 0 cubes. These are the 2 endpoints of the interval. And although we might have expected there just to be a single 1 cube, this would be this cube E. We also have these 2 other cubes, S1V0 and S1V1. These should be thought of as degenerate cubes. So S1V0 is, you can think of as a degeneracy of V1. This is, yeah. And so when we think about the sort of geometric realization of this cubical set, we primarily just have to work with these non-degenerate cubes. And even though a unit interval is finite dimensional, there are going to be cubes in this cubical model in all dimensions, and these are just going to come from the degeneracies of the 0 and 1 cubes. Now, we can look at another example, and this is the example of the unit square. Here there's going to be 4 non-degenerate 0 cubes. These are just the 4 vertices of the square. There's also 4 non-degenerate 1 cubes. But this, and there's also a single non-degenerate 2 cube. But there's also going to be a whole collection of degenerate cubes which come from these ones shown here. So, okay, now that we have some sort of cubical model for a unit square, how do we get this evaluation map that we wanted to obtain? In order to do this, we have to go through what's called the smooth geometric realization of these cubical sets. Symbolically, what's happening is we assign each element of the cubical set with a geometric cube, and then we glue everything together via these structure maps, these co-face maps, codegeneracy maps and co-connection maps that I discussed earlier. But I think it's also helpful to have a picture of what's going on. And while we look at this picture, we can also define the evaluation map. So for any p cube A in our cubical set, the evaluation map is going to be something from a geometric p cube into the geometric realization of our cubical set. And I'll explain how this goes as we work through this geometric realization. So we can construct this geometric realization in a hierarchical way. So we first just attach. We just have the 0 cubes, and then from the structure of the cubical set, we know that these 2 0 cubes are the face of this non-degenerate edge. So we can connect these 0 cubes by this edge here. Now, we also have these two degenerate 1 cubes, and these just get mapped to the 2 endpoints. So what's happening with this evaluation map is that we are mapping each of these disjoint cubes into where they go in the geometric realization. So now that we have 2 cubes, all of these will get mapped into either the vertices or the edge. So these 2 degeneracies of the vertices will go to the left and right, and we can map these degeneracies of the edge in 3 different ways. All right, so now that we have this evaluation map, we can discuss the cubical Chen construction for mapping spaces. So let's say that we have some finite cubical set model of our unit D cube. So in the case of D equals 2, we can think about the example from earlier. And Chen's construction follows very similarly to the one-dimensional case. This also has 3 steps. So first we choose a collection of differential forms on our underlying manifold, in this case Rn, and we choose one differential form for each p cube that we have in our model. We can compute the pullback of the tensor product of these forms along the evaluation map, which was given by our cubical set structure in the previous slide. And finally, now that we have a differential form on the p cube cross this mapping space, we can integrate along this p cube to get a differential form on the mapping space. And similar to the case of one dimension, we want to use certain 0 forms from this construction to define the mapping space signature. Okay, so now that we have the sort of a way to, some motivation for defining the signature, we can look at its definition. So symbolically, this is what the mapping space signature looks like. but I'll go through each of these components individually. So if we recall, with the path signature, this was indexed by a single multi-index I. The difference here now is that we're going to have two different indices for this mapping space signature. There's going to be what's called the forms index, and this should be thought of as some choice of forms that we are taking. So bold P consists of M functions from the finite set D to the finite set N, and these are order-preserving injections. So here I'm just using these types of functions to denote a basis of the Dth exterior algebra on Rn. And so in addition to this forms index, we also have a permutation index. So this is just going to be D permutations on M elements. Now here the domain of integration is this space I'm calling dm pi. So rather than taking an integral over a single m simplex, we're going to be taking a multi-iterated integral over d m simplices. But these simplices are also going to be permuted. So this is where this permutation index comes in. So each of these simplices are going to be permuted based on the permutations chosen in this permutation index. And just to clarify the notation here, bold T corresponds to just an element of this dm pi, and bold Ti corresponds to a choice of one coordinate from each of these m simplices. And finally, the integrand is going to be a Jacobian minor of our map X. So here P is going to be indexing a choice of D components of our map. The Jacobian of this is going to be sort of the Jacobian of the projection onto these D components is going to be a square matrix. So this JXP is just the determinant of this Jacobian. So these are what we're integrating are Jacobian minors. And at this point, we can sort of think about how this relates back to the path signature. In the case of D equals 1, this integrand is just going to be a determinant of a 1-by-1 matrix of just the derivative. And so this is where we recover the product of derivatives that we had with the path signature. In the case of D equals 1, we are just reduced to a single M simplex. And what might be a bit confusing is that we still have this permutation index, but it turns out that this is something that can be, this is additional information that can be quotiented out. So we're not losing anything if we don't consider permutations in the case of D equals 1. Now, in order to study sort of more analytic properties of this mapping space signature, we need some notion of metrics on our Lipschitz mapping spaces. And so one of the reasons we are working with Lipschitz functions or Lipschitz maps is the fact that we have Rademacher's theorem, which tells us that Lipschitz functions are differentiable almost everywhere. And this means that the Jacobian or the collection of Jacobian minors, which I'll call J of X, this can be thought of as an L infinity function from the D cube into the Dth exterior algebra of Rn. And since our mapping space signature was defined using only Jacobian minors, this introduces an immediate equivalence. This introduces an immediate invariance of our mapping space signature. So we say that two maps X and Y are Jacobian equivalent if all of their Jacobian minors are the same at every point in the D cube. And we will denote the space of Jacobian equivalence classes by Lipj. So here we can also return to the case of d equals 1 for a second. In this case, Jacobian minors just correspond to the component-wise derivatives of the path. So Jacobian equivalence is the same as translation equivalence, which is why we also denoted these translation equivalence classes of paths by Lipj earlier on. And so we can also define certain metrics for these paths, and we'll do this by sort of analogy with some metrics for paths. So two very common metrics to use for paths are the one variation metric. In the Lipschitz setting, this is just going to be the one norm of the difference between their derivatives. And we can think about the one variation metric as measuring the total difference between length increments. Another common metric for paths is the Lipschitz metric, which is the infinity norm on the difference between derivatives of the path. And we can think of this as measuring the maximum difference between infinitesimal length increments. And we can generalize this to the mapping space setting, where we define the Jacobian one variation metric as the one norm of the difference between their Jacobian minors. And this measures the total difference between volume increments rather than length increments. And similarly, we have this Jacobian Lipschitz metric for maps. And so with all of these tools, we can now turn to the first main result of this work. So similar to the case of the path signature, I can collect all of these different terms of our mapping space signature. So over all choices of the forms index and the permutation index into a single vector space. Or in particular, I can also look at a restriction of this into a Hilbert space. And it turns out that this mapping space signature has many of the same properties as we previously discussed for the path signature. So in particular, it's continuous with respect to the Jacobian Lipschitz metric. It has factorial decay at each level. This means that the norm at each degree decays factorially. And in particular, this implies that the image has bounded norm and therefore sits inside this Hilbert space. It's coordinate-wise reparametrization invariant. So recall from the path signature that this was one of the important properties in terms of applications, right? So in this case, if we reparametrize each coordinate independently by these phi j's, then the mapping space signature is also going to be invariant under this. We have a modified Chen's identity when the permutation index is fixed to be the identity. So this, what this means is that we don't have a Chen's identity. So this is the algebraic structure where that preserves concatenation. So while we don't have a full generalization of this identity, we're able to get a generalization on certain elements of this mapping space signature. And I should also highlight that this is quite a bit more complicated when we're working with higher dimensions, because when we work with, for example, maps from the unit square, there's now two different concatenation operations to consider. There's the horizontal concatenation and as well as the vertical concatenation. But what we do have is a generalized shuffle product structure. So in particular, linear functionals on the codomain of the mapping space signature, when we view these as continuous functions from these Lipschitz maps into R, this forms a subalgebra of the algebra of continuous functions. on Lipj. And so once again, this gives us our first indication that these mapping space signature terms behave very similarly to ordinary monomials on Rn. Oh, sorry. And finally, we also have some equivariance properties. So if we act on the codomain Rn by some element of GLN, then there's a corresponding action on this codomain. And there's also some interesting symmetries with the unit d cube. So BD is the hyperoctahedral group. This is the group of symmetries of the unit d cube. And we can also find a corresponding BD action on this codomain. But what we really want is some notion of universality and characteristicness that we started the talk off with. And in order to do this, we need to consider a sort of a variation of this mapping space signature. First, we need to perform a normalization of our signature, and we also need to append, do the step where what's called appending the parametrization. So here what we're doing is we're taking a map from the d cube into Rn, and we're just adding in the parametrization to the map itself. So this becomes a map from the d cube into Rd plus n. And I'll denote the parametrized mapping space signature as phi bar. And so the second main result of this work is that the normalized and parametrized mapping space signature is continuous, bounded, and injective. Injective, so these are all with respect to Jacobian equivalence classes of maps. It's also universal with respect to continuous bounded functions equipped with the strict topology. And it's also characteristic with respect to finite regular Borel measures on these equivalence classes of maps. So in particular, this is characteristic with respect to probability measures on the mapping space. So the implication of this result tells us that we can, if we were able to compute this and we wanted to use this as a feature map for sort of cubically parametrized data, that this would be both universal and characteristic, meaning that it's that we have some powerful properties in terms of machine learning. And so the last thing I want to do is to highlight the similarities between the monomial map. This should say the monomial map here. So highlight the properties between the monomial map, the path signature, and the mapping space signature. So in particular, what I want to highlight between these three columns here is that the main difference between these three is the type of elements that we're multiplying or integrating together. In the case of the monomial map, we're just taking tensor products of points. In the path signature, we're taking tensor products of length increments and then integrating them. And in our mapping space signature, we are similarly just looking at volume increments and integrating those. The properties of these three maps are also very similar. But okay, highlighted in red are the properties that aren't necessarily full generalizations of the path signature, but sort of intermediate generalization. So as I mentioned before, we don't have a full Chen's identity, but we have a modified variant. And in the case of the path signature, we were able to characterize the invariance of these signatures. So we said that two paths have the same signature if and only if they are tree-like equivalent. We don't have this full characterization of the mapping space signature at this point, but we do know that it's coordinate-wise reparametrization invariant. And lastly, we have these properties on universality and characteristicness. So here I am just looking at this in terms of compact subsets, in which case these three are can be stated in exactly the same way. So just to conclude and summarize, we used the topological framework of Chen's iterated integral construction to extend the signatures to cubical mapping spaces. And I think there's some very interesting directions for future work here. I mentioned very briefly that since the 90s, the path signature has been an important tool in the development of rough paths, and this has been used to study things like stochastic differential equations. And so one natural direction to continue studying this is to think about how we can go beyond the Lipschitz restriction. So rather than just looking at Lipschitz maps, we can look at maps which are lower regularity. We also went through this whole section on looking at Chen's construction in quite a bit of generality. And so while we only went through Chen's construction for mapping spaces in the Euclidean setting, so this is where the codomain was Rn, this actually holds in much more generality. We have Chen's construction for fairly general mapping spaces from some simplicial complex into some manifolds. So one question would be whether we can use these more general cochains in practice. And finally, just in the case that we discussed here, how can we extend signature methods in machine learning to higher dimensional parametrized data using the mapping space signature? So within the last 10 years or so, there's been a lot of activity in how we can apply the one-dimensional path signature to study sequential or time series data in machine learning. And there's now a variety of different methods to do this. And so I think it'd be very interesting to study how we can extend these methods to this higher dimensional domain. There's already some preliminary work in this direction. So there's a recent preprint by Joscha Diehl and Leonard Schmitz on developing a discrete version of this two-dimensional signature. There is also a paper that has looked at using these 2D signatures for image and texture classification, which has recently been published. And there's also a paper on using a similar idea, a similar notion of sort of generalization of signatures called regularity structures, and how we can use that with machine learning. And so with that, I would like to thank you very much for your attention. And just thank you very much for your attention.
Well, thank you for a very interesting talk. The floor is now open for questions. So, Darrick, I've got a naive question. In your abstract, you talked about cubical domains and such as images and videos, and I guess what the second thing you got here in your last slide talks about images and looking at signatures as giving you texture classification or something for two-dimensional images.
Yes. Yeah.
So is that what you're thinking about doing here, say in 3 dimensions? Or are you looking at stochastic processes on a cubical domain in 3D, like an MRI scan or something?
Yeah, I mean, I think that these could be very interesting applications to look into. So at this point, we were sort of just developing the theory of this, of these multidimensional signatures. And I guess this idea about images and videos is sort of motivation for sort of developing all of this theory. So there is this preliminary work that I cite. There is this work that I cite here, which does use some of the signatures, although there's currently sort of different definitions of 2D signatures that are used, which is also one of the reasons why we wanted to further understand the theory of these one particular definition, this one that we developed, and see if we could prove some of the properties that are that we have in the one-dimensional setting. So yeah, I think in the case of 2D, things like images or textures are interesting directions for applications. And like you mentioned, in 3D, we could be looking at sort of time-varying images, such as perhaps time-varying MRI scans, as you mentioned.
Yeah, I think that's a very interesting place. It's a place that needs some mathematics desperately. So,
yeah. Yeah, and I think there's still also quite a bit of work to be done here as well. I mean, one of I think one thing that needs to be studied at this point is the computation of these multidimensional signatures. The second paper, they were only able to use sort of a highly truncated version of these signatures. They're only looking at fairly low degrees of the signature, and it's at this point it's still these are objects that are still quite difficult to compute. But I think it'd be interesting to study whether there are good approximation methods or how we can or efficient algorithms to compute this in practice.
hearing that, let's thank the speaker for a very interesting talk.